Welcome to the course on power quality, and we were discussing on passive power filter. So, we have discussed the configuration, design and limitations. So, we like to discuss now the numerical problems on the passive filters like. So, starting from first problem, a single phase diode bridge rectifier is supplied from 230 volt 50 hertz AC mains as shown in the figure. The load resistance is of 100 ohm. Design a capacitive filter so that ripple factor of output voltage is less than 5%. With this value of the capacitor, calculate the average load voltage. So, you have a circuit here which consists typically of diode rectifier and have a capacitive filter and followed by the load. So, after typically designing and then giving the waveform, you just have this kind of the DC link voltage waveform, DC link current and then the supply current like. So, coming to numerical part of it, given that the supply voltage RMS voltage 230 volt, frequency of supply 50 hertz and load resistance is 10 ohm, ripple factor that RF is 5% and the amplitude of AC mains voltage is 230 volt, that is peak value of it is 230 into root 2, that is 325.269 volt, and the ripple factor is defined as RF equal to VAC upon VDC, and that is the relation after derivation comes 1 upon typically in bracket 4 FRC minus 1 into root 2, and typically while putting the value of all the factors. So, from this relation we can find out the value of capacitor comes around typically about 757.11 microfarad like, and the mean or average DC link voltage, from there we can find out VDC equal to VSM minus VSM by 4 FRC DC. So, that comes 303.78 like. So, coming to an example 2, a single phase diode bridge rectifier is supplied from 230 volt 50 hertz AC mains as shown in the figure here. The DC load resistance is of 30 ohm and the load inductance is your 10 millihenry. Design a DC side LC capacitive filter to show that the ripple factor of the output voltage is less than 10%. So, this is typically the LNC filter which we are designing for this diode rectifier to reduce, and after putting the value, these are the waveforms: supply voltage, typically the supply current, and then the DC link voltage and typically the DC link current also. So, solving this, the value of filter capacitor is computed as R d square plus 2 omega L square. So, that comes 10 upon 2 omega C CDC, or CDC will be from this relation comes 519.25 microfarad, and ripple factor is defined in terms of RF equal to VAC upon VDC. So, putting the value here of all these components, so ripple factor comes is 0.5 and it results putting this the value of the capacitor. So, inductor value comes 27.87 millihenry. So, that is the design of that LC filter. Now, coming to the third numerical problems in which we have designed the AC side filter. So, a single phase 3 branch shunt passive filter consisting of third, fifth and high pass filter is used to reduce the total harmonic distortion of supply current and to improve the displacement factor to unity of single phase 230 volt 50 hertz for diode bridge rectifier with an overlap angle of 30 degree, drawing 30 ampere constant DC current as shown in the figure, and calculate the fundamental active power drawn by the load, fundamental reactive power drawn by the load, elements value of the passive filter and current and VA rating of the passive filter like. So, here we have a typically the circuit of typical total system. So, we have a diode rectifier with the load and we have a typically the filter component here. So, putting all the value, we are able to see the waveform of passive current like and supply current and the load typically your rectifier current or load current like. So, after solving this, so it comes the numerical solution part of given that supply Vs RMS voltage is 230 volt, frequency 50 hertz, 230 volt AC supply with the overlap angle of 30 degree and DC link current is 30 ampere, and in single phase uncontrolled bridge rectifier with an overlap angle, the waveform of supply current is trapezoidal shape with the amplitude of DC link current, and since the trapezoidal wave of input current is odd and quarter symmetry cycle and half cycle symmetry, the supply RMS value is computed from the relation that IS equal to IL in bracket 1 upon root pi and area of the total waveform. So, just taking the derivation of the 1 upon root pi and the total area will be 4 into 0 to pi by 2 mu by 2 virtually and 2 IDC by theta by mu square plus 2 mu by 2 to minus mu by 2, that is IDC square d theta. So, from keeping this relation of mu and other data, here we are able to get typically you can call it the supply current typically 28.284 ampere like. So, trapezoidal waveform of input current is an odd and quarter symmetry and half cycle symmetry. The RMS value of nth harmonics current ISN RMS is computed as ISN Rn Bn upon by root 2 and calculating the Bn coefficient typically 8 by 2 pi 0 to pi f theta sin n theta d theta. So, keeping the value we get the ISN equal to IDC 8 divided by pi mu n square and into sin n mu by 2 in divided by root 2. Since it is a trapezoidal wave will not have a an coefficient. So, therefore, the RMS fundamental will be IL1 ISN and that will be typically putting n equal to 1 in that relation, IDC in bracket 8 by pi mu root 2 into sin mu by 2, that comes 0.89 IDC. So, it comes 26.7 ampere. The active power component of the supply current will be that IS1A equal to IL1A, that is IS1 cos mu by 2, that comes 25.79 and the input active power from the relation will be V into IS1A, that is VS1 VIS1 cos mu by 2. So, keeping the value of you can call it both the term. So, here the active power comes 5931.75 watt and the input reactive power comes Vs IS1 sin mu by 2. So, that comes keeping the value 1589.408 VAR and the mean output voltage, that is average output voltage will be root 2 by pi into Vs 1 plus cos mu, that comes 0.9 Vs 1 plus cos mu by 2. So, it comes 193.202 volt like. And the mean voltage is also as VDC equal to 2 root 2 Vs minus 2 omega Ls IDC by pi and therefore, the source inductance is estimated from this relation Ls equal to 2.312 millihenry like for that overlap angle which is given there like. Therefore, considering the source impedance as Ls equal to 3 millihenry, the source impedance is calculated as Zs equal to Jxs JLs into Ls. So, that comes J0.942 ohm and the voltage drop across the source impedance is your Zs IS1A. It by keeping the value of both, it comes 24.307 volt and the fundamental voltage across the load will be now Vs square minus Vz square under root of that. So, it comes to 28.712, that is approximately 230 volt like. So, passive shunt filter branch have a branch of shunt passive filter consisting of third, fifth and high pass damp filter. So, value of capacitor we can calculate it because there are 3 branches. So, the reactive power which we have calculated can be divided into equally 3. So, from this relation Q by 3 Vs square omega, from this we have a capacitance 31.879 microfarad and that is the same capacitance selected for third harmonic, fifth harmonic and higher order damp filter, that is a C, that is 31.879. So, this gives the 3 elements out of typically like your 7 element. Therefore, the value of inductor for third harmonic tuned by this relation, tuning this relation. So, 1 by omega 3, that is a 3 times omega 1 into C3, putting the value. So, L3 comes 35.314 millihenry and the resistance of the inductor for third harmonics from the quality factor, considering the quality factor of 50, it comes X3 by Q3. So, it comes 0.66 ohm. Similarly, we can have a now third harmonic in the load as third harmonic current IL3 from the relation this one harmonic component relation it is 8.106 and now we can find out third harmonic current in the supply from this impedance relation IL3 ZPF by ZPF plus ZS3 and putting the value it comes typically 1.859. So, that much is the current only flows into the supply, remaining go to passive shunt filter of third harmonics. The value of the inductor for fifth harmonics, tuned at fifth harmonics, is L5, that is 1 upon omega 5 square into C5. So, it comes 12.713 millihenry, and the resistance in of the inductor fifth harmonics filter is R5 equal to X5 by Q5 from quality factor. It comes 0.399 ohm, and the fifth harmonic current in the load, that is from this relation, I mean for n equal to 5, it comes 3.986, and the fifth harmonics in the supply current from the impedance relation IL5 to ZPF5 upon ZPF5 plus ZS5, giving the value, it comes only typically 0.336 from this value to this value, like also. Similarly, like coming to high pass filter, the value of inductor for high pass damped filter, which is tuned for seventh harmonic, is equal to L H equal to 1 upon omega 7 square CH. It comes 6.486 millihenry, and the damp resistance in parallel of an inductor of high pass damped filter, I mean calculated from this XH upon N, where quality factor is taken 1, it comes 14.264 ohm, and all the other load component to flow through the high pass damped filter. So, we can find out ILH, all the harmonics current of higher order, IL minus IL1 square minus IL3 as IL5 square. So, putting the value of all the higher order harmonics current is only 2.345 ampere, and the all higher order harmonic in the source current will be ISH, will be ILH into the impedance relation ZPFH divided by ZPF plus ZSH, and keeping the value of this. So, this comes typically order of 2.129 ampere, like and the TAD of supply current will be your third harmonic, fifth harmonic, and all higher harmonic divided by fundamental current. So, it comes like your 11.04%, like, and the TAD of the voltage will be like typically the drop of all these divided by fundamental voltage. So, it comes 6.553%, like, and your passive filter current will be IS square minus all the current going to. So, it comes 11.259 ampere, and the V rating of the passive filter will be IS Vs into IPF, because voltage across passive filter is same as supply voltage. So, it comes 2589.509 VA. Coming to example 4, a single phase 4 branch passive filter, third, fifth and seventh and high pass filter is used to single phase 220 volt 50 hertz system to reduce the TAD of supply current and to improve the displacement factor to unity. It has a load of thyristor bridge converter operating at 60° phi angle, drawing constant 25 ampere DC current as shown here. Calculate the value of elements of passive filter, the total harmonic distortion of supply current, the total harmonic distortion of terminal voltage, load and the current rating of the passive filter, and E the kVA rating of kVA rating to provide harmonics and reactive power compensation. Let the supply has a 5% source impedance, mainly inductive. So, these are typically the non-linear load with the thyristor and constant load current, and these are the passive filter we are designing, I mean for third, fifth, seventh and high pass. And after putting the value, these are typical waveform of supply voltage, then supply current, the load voltage, and then we have a typically load current and the passive filter current. So, coming to the solution part of it, given that the supply voltage of Vs equal to 20 volt RMS, frequency of supply 50 hertz with a source impedance of 5%, mainly inductive, feeding a non-linear load of 220 volt 50 hertz, single phase thyristor bridge converter with a constant DC current of 25 ampere at the 60° phi angle of its thyristor. So, in this system, the load current, harmonics and reactive power compensation is provided by the single phase 4 branch passive filter, third, fifth, seventh and high pass damped filter to reduce the TAD of the supply current and to improve the displacement factor close to unity. And the AC load RMS current will be IL equal to IDC, that is 25 ampere, and the fundamental RMS current will be IL1 equal to root 2 upon pi into IL. So, this is typically comes 22.5 ampere, and the fundamental active component of load current will be IL1 cos alpha. So, it comes like 11.25 ampere, and the fundamental active power of the load will be 1 equal to Vs1 IL1 cos theta 1, keeping the value, it comes 2475 watt, and the fundamental reactive power of the load will be Q1 Vs1 IL1 sin theta 1. So, putting the value, it comes like your 4286.8 VR, and the source impedance here is mainly inductive JXLS. So, is a 0.5% of the typically of the your load impedance 220 by 25. So, it comes 0.44 ohm, and the voltage drop across the source impedance, which that will current multiplied the source impedance, it is J 4.95 volt, and the fundamental voltage across the load will be VL equal to Vs square minus Vz square. So, it comes 219.94 volt, around 220 volt, and the passive shunt filter has a 4 branch shunt passive filter with third, fifth, seventh and high pass damp filter, and the reactive power of 4286.8 V are required by single phase thyristor rectifier had to be provided by the all 4 branches of passive shunt filter. Considering that all branches of passive filter has equal capacitor, therefore, the value of capacitor is typically calculated from this log Q upon 4 Vs square omega. So, it comes 70.48 microfarad, and all 4 have a same value of same 74. Third harmonic, fifth and seventh and high pass same as 70.48 microfarad, and therefore, the value of the inductor for third harmonic from this resonant relation L 3 comes equal to 16 millihenry, and the resistance of the third harmonic tuned filter will be X 3 R 3 equal to X 3 by Q 3. So, it comes putting the value 0.301 ohm, considering the Q 3 quality factor of this 50, which is in the range of 10 to 100 depending upon the design of inductor, and the third harmonic current in the supply will be I S 3 I L 3 into ZPF 3 divided by ZPF plus ZS 3. So, putting the value, it comes 1.667 ampere, and the third harmonic voltage at PCC will be I S 3 into ZS 3. So, it comes 2.2016 volt, and therefore, the value of the inductor for fifth harmonic tuned filter L 5 divided by typical putting the value of this in tuned relation 5.8 millihenry, and the resistance of the fifth harmonic tuned filter will be R 5 equal to X 5 by Q 5, that comes putting here 0.1806 ohm, considering Q equal to 50, and the fifth harmonic current in the supply will be I S 5 equal to I L. From this parallel relation, it comes 0.3683 ampere, and the fifth harmonic voltage at PCC will be your I S 5. So, it comes 0.81 volt, and therefore, the value of inductor for seventh harmonic from this two relation L 7 will be equal to 2.9 millihenry, and the resistance of the seventh harmonic tuned filter will be X 7 by 7. So, it putting the value, it comes 0.129 ohm, considering Q equal to 50, as it may be in the range of 10 to 100, and seventh harmonic passive filter current will be I S in the supply will be I S 7 with parallel relation, it comes 0.134 ampere, and seventh harmonic voltage at PCC I S 1 in ZS 1, putting the value, it comes 0.4144 volt. The value of the inductor for high pass damp filter tuned for seventh harmonics comes LH equal to tuned for ninth harmonic, it is 1.8 millihenry, and the resistance in parallel of the inductor of a high pass harmonic filter will be RH equal to QH XH upon QH, taking a QH 2. So, it comes 2.508 ohm, considering QH 2, and all the harmonics load current to flow to the high pass filter is calculated from ILH equal to IL square fundamental current square, then third, fifth and seventh harmonic, putting the value, it comes 5.649, and the filter current into the supply will be putting the value, it comes 3.0237 ampere, and the high pass voltage will be multiplying this 11.97 volt, and the TAD of supply current putting the all the current divided by fundamental, it comes 30.89, and the voltage TAD will be corresponding the value 5.55 percent like, and the current rating of the passive filter will be corresponding to this relation. It comes 22.055 ampere, and the V rating of the passive shunt filter V into IS, so it comes 4851.9 VA. Coming to the fifth example, a 3-phase diode bridge rectifier is supplied from 415 volt 50 Hz AC mains as shown in the figure below, and load resistance is R equal to 20 ohm. Designed a DC bus parallel capacitive filter, so that the ripple filter of the output voltage is less than 5%, and with this value capacitor calculate the average voltage DC like. So, this capacitor we are selecting, you can clearly see the how it looks like a voltage ripple in the output and the current drawn from the supply for such capacitor and load resistance like. So, the solution is Vs equal to 415 volt 50 Hz AC mains R 20 ohm and ripple filter 5%. So, amplitude of AC voltage will be Vs 415 root 2, that is 586.899 volt, and the design DC bus capacitance for a given ripple filter and 3 phase outbridge rectifier is defined as CDC from this relation 12 FR in bracket 1 plus 1 divided by RF into root 2. So, it comes like a typically your 1261.845 microfarad, and the average voltage is estimated VSM minus VSM upon 12 FRCDS. So, it comes 548.19139 volt. So, coming to the now the numerical example 6, a 3 phase diode rectifier, bridge rectifier is supplied from a 415 volt 50 hertz AC main as shown in figure. The DC load resistance is 10 ohm and the load inductance is 10 millihenry. So, design a DC side LC inductive capacitive filter so that the ripple factor of the output voltage is less than 10%, and this is typically the LC filter we are designing for this load. So, this is typically the your DC link voltage and DC link current and the load current, and typically the input supply current and the typically the supply voltage. So, coming to numerical part of the solution of the problem, the given that supply RMS voltage Vs equal to 415 volt, frequency of supply 50 hertz and resistance 10 ohm, inductance 10 millihenry and ripple factor of 10%, and the value of the filter capacitor is computed as R square plus 6 omega L square under root of that. So, keeping the value we get the CDC value typically of 248.63 microfarad, and ripple factor is estimated from the keeping the value of this, it comes typically taking that whatever given 0.1. So, you can find out the value of like from this ripple factor relation LDC equal to 1.8 millihenry. So, coming to the seventh numerical problems like a 3 phase 3 branch shunt passive filter tuned for 5th, 7th and high pass is employed to reduce the total harmonic distortion of supply current and to improve the displacement factor to unity for a 3 phase 415 volt 50 hertz fed 6 pulse thyristor bridge converter drawing a 100 ampere constant DC current at 30° fire angle of its thyristor as shown in the figure. Calculate the fundamental active power done by the load, fundamental reactive power done by the load, value of filter elements, total harmonic distortion of supply current, total harmonic distortion of load voltage, the voltage current and VA rating of the passive filter. Let the supply has a 5% source impedance, mainly inductive. So, this is the typical circuit of the load, that you have a thyristor converter with LC filter and then load, and you have a passive filter 5th harmonic, tuned for 5th harmonic, 7th harmonic and high pass. So, that you can see the supply current is sinusoidal in phase with the supply voltage, and this is the load is not affected and load voltage is also not affected, all these are, and this is the passive filter current like. So, coming to the numerical part of it, given that supply voltage is Vs equal to 415 by root 3 239.6 volt and frequency of supply 50 hertz with a source impedance of 5%, mainly inductive, feeding a non-linear load of 415 volt 50 a 3 phase thyristor bridge converter with constant DC current of 100 ampere at 30° fire angle. So, in this system the load current, harmonics and reactive power compensation is provided by 3 phase 3 branch shunt passive filter 5th, 7th and high pass damp filter to reduce the TID of supply current and to improve the displacement factor close to unity, and the AC load RMS current is equal to IL IDC into root 2 by 3. So, that comes 81.65 ampere, and fundamental RMS input current of thyristor bridge will be IL1 equal to under root 6 by pi into IL, given the value it comes 77.98 ampere, and the fundamental active component of current will be corresponding to IL1 equal to I1t cos alpha. So, keeping the value of fire angle of 30° and current that comes 67.52 ampere like, and fundamental active power of the load will be 1 TVS 1 IL1 cos theta 1, and given the value of this it comes like 48,536.0805 watt, and the fundamental reactive power of the load will be Q1 equal to TVS 1 IL1 sin theta 1, and giving the value it comes 28,036.01 VAR. That is the reactive power have to be provided by the passive filter, and the source impedance that is mainly 5%, keeping the value of all it comes 0.14868 ohm, and the voltage drop across the source impedance is your current multiplied this impedance that comes J 9.91 volt like, and the fundamental voltage across the load is VL equal to Vs square minus Vz square, that keeping the value it comes 239.19, which is very close to typically of 239.2 volt like and the passive, now the passive shunt filter has 3 branch shunt passive filter for 5th, 7th and high pass damp filter, and the reactive power required by this is by converter is 28,026.01 kVAR required by the 3 phase thyristor rectifier had to be provided by all 9 branches of the passive shunt filter. So, considering that all the branches of passive shunt filter has equal capacitor, therefore, the value of capacitor is as C equal to Q 1 upon 9 VSC square into omega. So, keeping the all value, it comes 172.75 microfarad, and which is equal to all 3 equal, means C 5, C 9 and C H equal to C equal to 172.75 microfarad. Now, coming to the calculation of the other element of the passive filter, that is the value of the inductor for fifth harmonics tuned filter is alpha equal to 1 upon omega 5 square C 5. So, that comes 2.35 millihenry, just keeping the value of that, and the filter resistance of the fifth harmonics tuned for X 5 by Q 5 tin quality factor of 30. So, it comes 0.1229 ohm, and the fifth harmonic current in the supply will be IL 5 ZPF upon ZPF into your ZS 5. So, keeping the value, it comes typically order of only 2.5765 ampere, and the fifth harmonic voltage drop at PCC will be IS 5 into ZS 5. So, it comes 1.89 volt only. Now, the value of the inductor for seventh harmonics tuned filter will be L 7 equal to 1 upon omega 7 square C 7. So, that comes 1.198 millihenry, and the resistance for seventh harmonic tuned filter will be R 7 equal to X 7 by Q 7, that we take the 30. So, that value will be 0.0877 ohm, and the seventh harmonic current in the supply will be IL 7 IS 7 equal to IL 7 into ZPF 7 divided by ZPF 7 ZS 7, and keeping the value, it comes 0.948 ampere like, and the seventh harmonic voltage at the PCC is equal to IS 7 ZS 7. So, keeping the value, it comes 0.9744 volt, and the value of inductor for high pass damped filter for 11th order will be 1 upon 11 square into CH. So, it comes 0.4852 millihenry, and this resistance in parallel of inductor for high pass damped filter is equal to X H upon QH. So, taking quality factor of 2 and putting the value, it comes 0.835 ohm, and all the harmonics current, harmonic load current to flow into the high pass damped filter. So, we can find out the load, all higher order load harmonic current equal to IL square minus IL 1 square, IL 5 square, IL 7 square and root of that, and keeping the value, it comes like 14.78 ampere like, and the your all higher harmonic in the source will be ILH into ZPF, putting the value, it comes 6.837 ampere like. So, high pass harmonic voltage at the PCC is equal to ISH into ZH, and it comes 11.035 volt, and your total harmonic resistance for supply current taking all harmonics divided by IS1. So, it comes 10.91 percent, and the TID of voltage will be again the voltage of for all the harmonics will be 4.69 percent like, and current rating of the passive shunt filter is it's just all current going to passive filter, then total RMS load current minus the fundamental active fundamental of power, then the fifth, seventh and 9 your high pass. So, it comes 45.309 ampere, and the V rating of the passive shunt filter is your 3 into VPF into IPF, and giving a value, it comes 32,568 VA like. So, coming to the 8th numerical problem, a 3-phase 1 branch shunt passive filter 11th order high pass damped filter is employed to reduce the TID of the supply current and to improve the displacement factor to unity of 3 phase for 15 volt 50 hertz non-linear consisting of 12 pulse thyristor converter with a 200 ampere constant DC current at 30° phi angle of its thyristor as shown in figure, and the converter consists of ideal transformer with single primary star connected winding and 2 secondary winding connected in star and delta with same line voltage to provide 30° phase shift between the 2 sets of 3 phase output voltage. The 2 6 pulse thyristor bridges are connected in series to form this 12 pulse AC/DC converter. Calculate a fundamental active power drawn by the load, fundamental reactive power drawn by the load, value of filter elements, total harmonic distortion of supply current with the passive filter, the total harmonic distortion of voltage with passive filter, voltage, current and V rating of the passive filter. Let the supply has a 5% source impedance, mainly inductive. So, the typical circuit, this 12 pulse converter, here we are fitting like a passive filter. This is similar to like a what we are having like a HVDC. So, we are putting 11th harmonic high pass filter, and this is the, you can call it the supply current supply voltage, supply current, then the load voltage which is not affected, and the load current, that is a 12 pulse converter step current, and this is the passive filter current, which consists of course these all harmonics plus the fundamental reactive power current also. That is the only reason, that is the reason reactive power is compensated by this passive filter also. So, coming to the solution, given that Vs equal to 415 by root 3 to 39.6 volt and frequency of 50 hertz, and ID your DC side current is 200 ampere and fire angle 30 degree. So, in 3 phase 12 pulse thyristor bridge converter, the waveform of the input AC current is step waveform, as first step of pi by 6 angle form alpha to pi by 6 and input current magnitude IDC by root 3, and the second step is pi by 6 angle from alpha to pi by 6 to alpha plus pi by 3 and input current magnitude of IDC in bracket 1 plus 1 by root 3, and the third step of pi by 6 angle from pi by alpha plus pi by 3 to alpha plus pi by 2 and the input current magnitude of IDC in bracket 1 plus 2 by root 3 in bracket, and it has all 4 symmetrical segment of such types like. So, therefore, the RMS current of 12 pulse thyristor converter will be your 1.55735 IDC, that is 315.47 ampere, and the moreover the RMS of 12 pulse converter fundamental current will be equal to 2 root 6 by pi into IDC, that is a 1.559 into IDC, that is come 311.879 ampere, and the active power component of supply current will be IS1 cos theta 1, that is IS1 cos alpha. So, it comes like a 270 wrong, like kindly correct it. Okay. This will 155.94 into your coming into your, yeah, it is okay. This is the value here, this is the correct, like it comes like a 270.095 ampere like, and the RMS active power done by the load will be your P equal to active power done by the load will be P equal to 3 Vs1 IS1 into cos theta 1. So, it comes 194.145 kilowatt, and the fundamental reactive power will be your 3 Vs IS1 sin theta. So, putting the value it comes 112.089 kVA, and the source impedance is your ZXH 5% of so base impedance. So, it comes 0.038 ohm, and the voltage drop across the source impedance is your J 270.0 into 0.038, that comes J 10.257 volt like, and the fundamental voltage across the load is well equal to root Vs square minus Vzs square, that comes to 39.38 or very close to the supply voltage 239.6 volt. And now, the passive shunt filter has one branch shunt branch passive filter 11th order high pass only to M. So, that comes C equal to for 3 phase 3 branch. So, it comes Q1 upon 3 Vs square into omega, putting the value it comes 2071.659 microfarad, and that is the typically for the capacitor for all 3 phases, and the value of the inductor for tune for 11th harmonic, I mean 1 upon omega square 11 square into Ch. So, it comes your 0.040 milli Henry, and the damp resistance of the parallel into the inductor for high pass is x h upon q h. So, taking is a quality factor of 2, it comes 0.07 ohm, and all the other harmonics load current to flow into the high pass damp filter. So, it is ILH equal to IS minus IS 1 square. So, you look into that, it comes 47.464 ampere, and the current flowing into the harmonic current flowing into the source of all harmonic from this impedance relation, it comes only 7.839 ampere, and the high pass filter voltage will be at the point of ISH into ZSH, in the value it comes only 3.277 volt, and the TAD of the supply current will be is reduced from typically from 15% to ISH square upon IS, it is only 2.9 percent, and the TAD of the voltage when from voltage drop divided by Vs1, it is only 1.368% like. So, that is the design of high pass filter corresponding to 12 pulse converter for considering 11th harmonics and above, and your current rating of the passive filter is from this relation ISH square minus the fundamental active current minus the your current which is flowing into the source typically into shunt. So, that comes 162.815 ampere, and the voltage rating of passive shunt filter will be your typically 3 into voltage across the passive filter, then the current of passive filter. So, it comes 117.031 kVA. Coming to example 9, a 3-phase 3-branch shunt passive filter tuned for 11th and 13th and high pass is employed to reduce the THD of supply current and to improve the displacement factor to unity of 3-phase 415 volt 50Hz non-linear load consisting of 12 pulse thyristor bridge converter with 200 ampere constant DC current, 60 degree firing angle of its thyristor as shown in figure. This converter consists of ideal transformer with single primary star connected winding and 2 secondaries connected in star and delta with the same line voltage to provide 30 degree phase shift between 2 sets of 3-phase output voltage. So, 2 6-pulse thyristor bridges are connected in series to form a 12-pulse AC/DC converter. Calculate A, fundamental active power drawn by the load, B, fundamental reactive power drawn by the load, C, the value of filter elements, D, the THD of supply current with the passive filter, and E, the THD of load voltage with the passive filter, F, the voltage current and VA rating of the passive filter. Let the supply has a 5% source impedance, mainly inductive. And these are typically the circuit of the system that we have a 12 pulse converter with a star delta secondary side with the series connection and passive filter 11th, 13th and high pass. So, after designing and putting all the values, here we have a supply voltage, supply current which have a unit in phase, and these are the typically load voltage and these are the load current and passive filter current. So, coming to the solution, given that supply voltage of 415 by root 3 to 39.6 volt and frequency of supply 50 Hz and DC current of 200 ampere and firing angle of 60 degree. In 3-phase 12 pulse thyristor bridge converter, the waveform of the input AC current is a stepped waveform of as a first step of pi by 6 angle from alpha to alpha pi by 6 and input current magnitude IDC by root 3, and second step of pi by 6 angle from alpha by 6 to alpha pi by 3 and input current magnitude of IDC in 1 plus 1 by root 3, and third step of pi by 6 angle from alpha pi by 3 to alpha pi by 2 and the input current magnitude IDC 1 plus 2 by root 3, and it has a all 4 symmetric segment of such a step. Therefore, RMS value of 12 pulse converter input current is IS equal to IL equal to 1.557 IDC, so it comes 315.47 ampere. Moreover, the RMS current of 12 pulse fundamental AC current will be IS1 equal to IL1, putting the value 2 root to 6 by pi into IDC, so it comes 311.86 ampere, and active power component of supply current IS1 is putting the value, it comes like 155.9393 ampere, and active power drawn from the load will be 3 into IS1 I cos theta 1, so it comes 112.08895 kilowatt, and the fundamental reactive power drawn Q1 3 Vs into IS1 side theta 1, it comes 194.1437 kVr, and the source impedance is JXS, that is 5% of this, so it comes 0.037975 ohm. The voltage drop across the source impedance is the source impedance multiplied the current, so it comes J 5.922 volt, and the fundamental voltage across the load will be L equal to Vs square minus J, so it comes to 39.53, so it comes to 39.6 volt. Now, coming to C part, the passive shunt filter has a 3-branch filter, 11th, 13 and high pass damp filter, and reactive power of 194 kVr required by the 3-phase thyristor bridge converter have to be provided by the 9 branches of passive shunt filter, considering that all the branches of passive filter have equal capacitor. Therefore, the value of capacitor is C equal to, putting the value here. So, we get it is 1196.68 microfarad, and all capacitors are equal same as 1196.68 microfarad. And coming to the, therefore, the value of the inductor for 11th harmonic from tune relation for this L11 will be your 0.07 millihenry, and the resistance of the inductor for 11th tune filter R11 will be X11, that is putting the value Q equal to 20, so it comes 0.0121 ohm, and the 11th harmonic current in supply will be IS11 equal to, from this parallel relation it comes 0.821 ampere, and 11th harmonic voltage will be your, putting the value it comes like 0.343 volt, and therefore, the value of inductor for 13th harmonic from tune relation of L13 will be 0.0502 millihenry, and the resistance of the inductor for 13 harmonic tune filter R13 will be X13 by Q13, putting the value Q factor of 20, so it comes 0.01024 ohm, and the 13th harmonic current in supply will be IS13 with the parallel relation, it comes 0.497 ampere, and the 13 harmonic voltage with the current multiplied the impedance of source for 13th harmonic, it comes 0.2455 volt, and the value of inductor for high pass damped filter for 23rd harmonics, that I will tune for 13th harmonic. So, it comes 23rd harmonic, it comes 0.016 millihenry, and the resistance in parallel to the inductor of high pass damped filter will be XH into this. So, taking quality factor 2, it comes 0.0579 ohm, and all harmonic currents have to flow through this. So, all harmonic current other than load current minus fundamental, the 11th 13th, it comes 29.54 ampere, and the current going to the supply for all harmonic current, I mean calculated form, it comes 1.958 ampere, and the voltage, I mean high pass harmonic filter at PCC will be VSH equal to current multiplied the impedance. So, it comes 1.71 volt, and the TAD of supply current for 11th 13th all high pass divided by fundamental, it comes 1.4%, and the voltage TAD will be then the drop of all divided by fundamental voltage, it comes 0.74% like, and the current rating of passive shunt filter will be equal to your fundamental current minus your fundamental current active current, then the 11th harmonic source 13th harmonic, and all it comes 274.14 ampere, and the V rating will be corresponding to 3 into voltage, phase voltage into current. So, putting the value, it comes your 197 kVA. Coming to 10th problem, as example, an industry is fed from electric power from 3 phase 33 kV 50 hertz AC mains. The data of the supply feeder are as short circuit level 150 MVA and X upon R ratio is 3, and a step down transformer is placed between the AC mains and the industry with a rating of 15 kVA of 33 kV by 440 volt with the resistance of 2%, X equal to 4%, reactance of 4%. It is supplying the linear and non-linear load as shown in the figure below. If an AC capacitor bank is used at the PCC for power factor correction of the industry, calculate the rating of this capacitor filter capacitor bank, which may excite the parallel resonance at the 5th harmonics with the supply system, and this is the typically you can call it supply system, the source impedance, then the transformer with the capacitor, and this is the like all transform impedance of the source towards on the secondary side or low voltage side of the transformer, and the transformer reactance, resistance reactance, short circuit impedance, and then the capacitor here, which can be lumped together. So, equivalent circuit comes from that. So, we can find out from typically the corresponding resonance condition virtually. So, coming to a numerical part of it, given that a 3 phase 33 kV 50 hertz AC mains has a feeder with the data as short circuit current level of 150 MVA and X upon ratio of 3, a step down transformer is placed between AC mains and this industry with a rating of 15 kVA 33 kV by 440 volt, resistance of 2% and reactance of 4%. Here the feeder impedance is given in terms of short circuit MVA, that is MVASC, and XR upon ratio and voltage level. The value of the feeder resistance and reactance in ohms are calculated from the relation of your kV square divided by MSC. So, putting the value here cos X upon this. So, it comes resistance of the supply comes 2.2958 ohm, and similarly reactance comes 6.874 ohm from keeping the value in the relation, and these data of the feeder in ohms are referred to LV side of the transformer. So, these are divided by turns ratio square. So, it comes like 0.0041 ohm, and reactance comes on the second side say 0.0012 ohm, and the equivalent circuit parameters of the transformer referred to the secondary are calculated similarly. Then per unit multiplied the base impedance. So, it is 0.00258 ohm, and the reactance on secondary side comes 0.00516 ohm, and the total equivalent circuit parameter of the system shown in figure are as like total resistance on the low voltage, your supply impedance, the transformer resistance, and supply feeder resistance. So, it comes total 0.00299 ohm, and total reactance will be your feeder reactance plus the transformer short circuit reactance. So, it comes 0.0063 ohm, and the value of from this reactance is the LT inductance will be LT upon 2 pi f. So, it comes 20.3167 microhenry, and rating of the capacitor bank to excite the parallel resonance at 5th harmonic the supply system is equal to total impedance of equivalent source in the figure at any frequency can be calculated Z I equal to R T plus omega A corresponding to the frequency L T divided into minus j upon omega A C and divide by R T plus j omega L T minus this, and under the parallel resonance the denominator of the impedance must be minimum value and it should be the minimum value of the at frequency omega r. So, when the inductance and reactance are equal, a capacitive reactance, so you can find out omega r L T equal to 1 upon omega r C. So, we can have a resonance frequency 1 upon under root L T C and F r equal to omega r upon 2 pi. So, that is come 1 upon 2 pi into under root L T C. So, from this relation the equivalent capacitance of the capacitor bank is as follows. I mean putting the value in this, I mean this comes at 19,948.39 microfarad and Xc of it is 0.157 0.15957 ohm, and the kVr rating of this will be typically from putting the value of this capacitor and voltage here. So, it comes like 1213.286 kVr. So, if that much kVr capacitor is kept, certainly you will have a resonance problem like. So, coming to now typically another numerical problem interrelated with that, there is 11th problem. Industry is fed from electric power from a 3 phase 3350 hertz AC mains. The data of the supply feeder are as short circuit impedance level is 50 kVA XR upon 3 and a step down transformer is placed between the AC mains and the industry with a rating of 1500 kVA 33 kV upon 440 with the resistance of 1% X equal to 5%. A 3 kVA 440 volt 3 phase thyristor converter fed DC motor drive is used in this industry along with the other linear load as shown in the figure. If a 1000 kVR capacitor is used at the point of common coupling for power factor correction of the industry, calculate the PCC voltage and its total harmonic distortion without capacitor bank, PCC voltage and total harmonic distortion of capacitor at its TAD with the capacitor bank, and current in the capacitor bank, harmonic spectrum of AC current of the 300 kVA 50 hertz 3 phase thyristor converter fed DC type is given in the table, next table. So, this is the you can call it harmonic current for the load of this 6 pulse converter. So, 5th harmonics current is given, 7th harmonic, 11th harmonics, 13 and 17th harmonics currents are given here in ampere. That is the data given, and this you have typically the source, then the impedance and the transformer, and then the capacitor bank value is given. The equivalent of this on LT side, on this side is equivalent, and then we can calculate equal, and then we put typically the value corresponding to this capacitance of 1000, and you can find out the typical kind of here the resonance problem like okay. You can see the current in supply how it is distorted and how the capacitor current is also distorted because of the resonance, and of course, load current is not affected like. So, let us come to numerical part of it. Given that a 3 phase 33 kV 50 hertz AC mains has a feeder with the data short circuit current level of 150 MVA with the X upon ratio 3 and a step down transformer is placed between the AC mains and this industry with a ratio of 15 with the rating of 1500 kVA 33 kV by 440 and resistance 1%, reactance of 5%. A 300 kVA 440 volt 3 phase thyristor converter bridge converter fed DC motor drive is used in this industry along with the linear load. A 1000 kVR capacitor bank is used at the PCC for power factor correction of the industry. The total system and equivalent circuit are given here. So, total impedance, total system and its equivalent circuit shown in figure. Here the feeder impedance is given in terms of short circuit current level and XR ratio, and value of the feeder resistance and reactance are calculated. So, resistance of the feeder from this relation is come 2.2958 and the reactance come from this relation 6.877 ohm, and these data on the feeder are to be referred on LV side of the transformer. So, we are just taking turns ratio square. So, it comes 4.0040814 ohm and reactance is your 0.0012244 ohm. Now, the equivalent circuit parameter of the transformer referred to the secondary side, that is the given 1% resistance. So, it comes 0.001291 ohm and reactance of the transformer short circuit reactance as a 5%. So, it comes 0.006453 ohm, and the total equivalent circuit parameters of the system shown in that figure is come feeder resistance plus the transformer reactance on the secondary side comes 0.00169914 and the reactance total will be calculated 0.00767 and the inductance of this will be 24.45138 microhenry. an equivalent reactance of the capacitor bank. I mean, from this relation it comes like a typically your 0.936 and capacitance 116,449.97, and the magnitude of fundamental current of the converter supplying it typically from here 300 either DC ring current, I mean from this kVA, so it comes like a 393.65 ampere, and the PCC voltage and HTAD without capacitor bank are computed as follows. So, without capacitor bank the supply impedance is computed as harmonics. The voltage drop across each harmonics current of the load is computed by multiplying the supply impedance and that of harmonic frequency and harmonic current, and these are computed, values are given in table. So, these are from that relation, these are the harmonics order, this is the harmonic frequency, this is the resistance, I mean the total resistance, this is the reactance, and this is the impedance, total impedance, and this is the harmonics current, and this is the harmonic voltage at the point of common coupling, because you have to multiply this with this, so you will get this harmonic voltage, and from this you can find out the RMS value of this typically from harmonic current from this. So, it comes like a total RMS current is your 403.45, and the TAD of it, I mean if you calculate from total RMS minus this square, total RMS we calculated earlier, so it comes like a 21.27%, like that is the TAD of the current, and the TAD your RMS voltage at PCC, I mean if you calculate from this relation it comes 24.063 volt. So, it does not differ much from the typically from fundamental of 254 volt. Like the total harmonic distortion in PCC voltage, that is this Vs square minus Vs1 by Vs1, and it is only 1.57% is the total harmonic distortion of the voltage caused by this nonlinear load at the point of common coupling without capacitor. Now, we come PCC voltage and its total harmonic distortion with capacitor bank. So, now parallel impedance Z I at each frequency is calculated from the capacitor value, and then harmonic voltage across the parallel impedance, and then capacitor current from the that harmonic voltage. So, these are calculated and given in table. So, now you can see harmonic order, harmonic frequency, the resistance, reactance, total reactance of the circuit resistance and all that. This is the total impedance, this is the for different frequency the capacitor, that I mean 1000 kVR capacitor reactance correspond to these harmonics, and this is the total impedance along with the capacitor of this circuit, this is the harmonic voltage. Now, these are the harmonic voltage. When you multiply this impedance with this harmonic, so you can see this is really coming your 5th harmonic voltage is coming substantial, and other harmonic voltage and the capacitor current corresponding to, because of this high voltage for 5th harmonic, the current also corresponding to 5th harmonic in capacitor bank goes quite high, and of course, these other harmonics current are also more. When these are amplified, you can say from 70 ampere it goes this much, from 40 it goes 82, 20, 25, 10 to 11 and 3 to this. So, all are amplified, but 5th is very extremely amplified, 7th is little more amplified, and you can find out RMS voltage PCC, I mean from this all the voltage harmonics you can calculate typically from these harmonic voltage. So, TAD voltage comes to 61.04, and the total harmonic distortion of the voltage comes like typically putting the value here, it comes 23.70 volt percent of total harmonic distortion in the voltage, which was hardly around less than 2% earlier, and the current in the capacitor bank calculated now. This is fundamental current, and you have a fundamental current, then the 5th harmonics current in capacitor, 7th harmonics another, and it comes like in place of your 1332, it comes 3566, and which clearly say there is a resonance. So, capacitor current is 153% of rated current because of the parallel resonance of this power factor correction capacitor with supply impedance, and this magnitude of capacitor current is likely to blow the fuse of the capacitor bank as Baker to tip and may also damage the capacitor bank. So, this is the condition of resonance what really we have demonstrated through numerical example like Now, coming to a 12th problem, a industry is fed from electric power from a 3-phase 3350 Hz AC mains that out of supply feeder are edge like a short circuit current level of 150 kVA x upon a raise of 3. A step down transformer is placed between the AC mains and this industry of 1500 kVA 33 kV by 440 with the resistance of 1% and reactance of 5%. A 300 kVA 440 volt 3-phase thyristor converter which DC drive is used in this industry with other linear load, and if 1000 kVR capacitor bank is used at the PCC with for power factor correction, it tuned to lowest harmonic 5th harmonic passive shunt filter, calculate the parallel resonance frequency, the filter harmonic spectrum, current of filter, PCC voltage and TAD of passive filter, the RMS capacitor voltage, harmonic spectrum of AC mains current of 300 kVA of this is given, in table 1. So, it is the same problem what we demonstrated, but now we are tuning this capacitor corresponding to fifth harmonic filter. So, these are harmonic currents corresponding which is given for the given non-linear load, and this is the again the same circuit, I mean source impedance, and then the transformer, I mean, and then the typically now it's in place of capacitor we have tuned for fifth harmonics now, lowest harmonic that is present in this linear non-linear load along with the linear load. So, that is the equivalent, you can call it the total reactance here, and this is the capacitor of that we are keeping, and now we are keeping an inductor for tuning it for lowest harmonic, that is fifth harmonic, and that is the total circuit. And you can see now clearly the current is improved, like I mean you can see clearly current is improved at kind of unity power factor, and it is a sinusoidal current, and then this is the voltage, this is the load current, and this is the your capacitor filter current here, which are not disturbed, but mainly because it is a reactive current like. So, by tuning it you can avoid the kind of resonance. Let us come to the numerical part of it. Given that a 3 phase 33 50 hertz AC mains has a feeder with the data edge short circuit current level of 150 kVA, XR upon ratio 3, and step down transformer placed between the AC mains and this industry with the rating of 1500 kVA 33 kV divided by 440 volt with the resistance of 1%, reactance of 5%, and 300 kVA 440 volt 3 phase thyristor converter bridge for DC motor drive is used to in this industry along with the other linear load, and 1000 kVA capacitor bank is used at the PCC for power factor correction in the industry, and total system and equivalent circuit are given figure. So, here the feeder impedance in terms of short circuit I mean and voltage level, these value of feeder resistance and reactance are calculated as. So, resistance of the feeder from this relation is calculated 2.2958 and reactance is calculated 6.8874 ohm. These data of the feeder are referred to LV side by dividing turns ratio square. So, it comes 0.004081 4 ohm and reactance comes 0.001224 ohm, and the equivalent circuit parameter of the transformer referred to the secondary even for total short circuit resistance. It is referred to secondary 0.001291 and reactance to the secondary it comes like a 0.006453 ohm, and the total equivalent circuit parameter of the system will be your feeder resistance, then the transformer resistance. So, it comes 0.00169914 and the reactance total will be is your 0.0767777 ohm, and inductance is your 24.45138 microhenry. So, equivalent reactance of the capacitor bank we can calculate XC at fundamental frequency, it comes typically 0.1936 and the capacitance is of it comes 16,449.97 microfarad. The passive shunt filter tune are tuned at a 5% to 10% lower than actual harmonic present to be reduced in this. So, normally fifth harmonic filter tuned for 4.7th harmonic order of the supply system, therefore, fifth harmonic filter at 4.7th order harmonics of the supply system, and the inductor filter is calculated from this relation. I mean typically for this passive. So, capacitance is given and this is tuned for 4.7 harmonic of fundamental. So, the inductance of this passive filter comes 27.887 microhenry and the reactance of this comes 0.0087597 ohm like. So, now magnitude of fundamental current of the converter supplying DC motor, I mean that is given 300 kVA. So, divided by the voltage, that is fundamental current 393.65 ampere, and the parallel resonance frequency with the passive tuned filter can be calculated. I mean the total equivalent circuit shown in the figure, that is from ZI, and this is the total impedance of resistance, then inductance, total inductance, and the filter inductance. This is the filter impedance, this is the impedance of the source along with the filter and all that, and then I mean sum of both, that is a parallel one, and LF is the value of filter inductor. So, under the parallel resonance, the denominator of impedance must be minimum of the imaginary part of the denominator equal to 0. It will be minimum value at the frequency omega r when the inductance reactance is equal to capacitive reactance. So, we can just put the value here, I mean along with the LT we put LF, and from this capacitor we get the resonance frequency, and this resonance frequency in hertz is now 171.57. So, in place of fifth harmonics now it is reduced to typically order of this frequency. So, the parallel resonance phenomena is avoided from fifth harmonics and it is shifted to occur the parallel resonance at value less than the lowest order harmonic present in this harmonics producing load, and at 3.43 order of harmonics. Earlier it was fifth harmonic, now it is reduced to this. Therefore, this shifting of parallel resonance frequency to much lower frequency, that is 3.43 order of harmonics corresponding to 171.51 hertz in in place of 250 hertz. Then the harmonic present in the load avoids the amplification of harmonic current and PCC voltage is minimized in the system. So, now we can have a filter harmonic current spectrum and current of the filter can be calculated. So, the filter current fundamental current will be corresponding divided by nominal voltage divided by the impedance of the filter at fundamental frequency. So, this comes typically order of this 1374.13, that is the fundamental current going into this, that is mainly the capacitive current like also, and current flowing because at fundamental frequency it is a capacitive current, it behave as a capacitor. So, current flowing into the harmonic filter at any other frequency can be calculated from current going into filter, that is the total current harmonic current, and then the impedance of this typically which is going to be this is the voltage multiplied the filter impedance. Okay. This is the your source impedance multiplied the filter impedance divided by total impedance divided by filter impedance, that comes your harmonics in the filter. So, just now under this condition harmonic currents in the passive filter is calculated, and the harmonic filter current comes fundamental current RMS current comes your total current of filter RMS including your fundamental, then the fifth, then seventh, then 11, 13 all harmonics. So, it comes 13758 ampere in the filter, and the total current of the capacitor is you are having this 11312, and you can call it RMS current percentage of the this like typically and capacitor. So, you keeping the value it is only 104.83%, it was earlier in resonance 153%, which is reduced to hardly 104.834%. So, that this passive filter current flowing through the capacitor is only 105% of this rated current, which is well within the considered rating, and this is the typical value. Now, we can see the calculation for all harmonics corresponding to. So, this is the harmonic order 5th, 7th and all. These are total resistance of the circuit, reactance, then total impedance, this is the capacitance impedance, that is the filter inductance impedance, and these are the harmonics currents which are of the load. This is the typically you can call it the harmonic filter current, this is the source harmonic current, this is the harmonic voltage at the point of common coupling, this is the typically capacitor voltage, harmonic voltage, and this is the total voltage across the load of harmonic. So, now the PCC voltage and TAD can be calculated with the passive filter for calculation of the voltage distortion, harmonic current flowing to the supply system are given here in the table. From this relation we can find out IS is equal to, so the fundamental PCC voltage 415 by root 3 254, and the harmonic voltage at different harmonics is IS into this impedance, and the equations are used to calculate the harmonic voltage to find out the PCC voltage. If you keep the all from that table all voltage, so it is only 3 all currents of harmonics, it comes 394.187 ampere only, and the shunt filter source current from this you can calculate fundamental voltage, and this will be the typically the harmonic voltage, and these equations are used to calculate the harmonic voltage at PCC which are given, and you can have a total RMS current going to typically into the supply system, and the TAD of this is only now of supply current is 5.22%, and the RMS value of the typically PCC voltage is calculated from this all harmonic voltage plus this. So, this is 254, which is not much deviating from the nominal voltage, and the TAD of PCC voltage if you keep it is only 0.1518%, and you can see that resonance is avoided as well as it is giving the right solution for reduction of. So, this TAD distortion PCC voltage is 0.5186% and reduced from 2.23% without the filter, and this TAD distortion PCC voltage of 0.5186 is also reduced from 23.7 in case of power fraction capacitor which was under resonance. So, in resonance this was the TAD, without filter this is the TAD, and with now with passive filter this is the TAD. So, this is you can clearly see even from without the filter it is reduced to this, but from resonance it gone to this, and that is reduced to this like and the total RMS capacitor voltage will be fundamental can be calculated. So, these are fundamental current of the capacitor, and you can have now typically fundamental current of capacitor 137.413 ampere, and fundamental capacitor voltage you can calculate from here. So, it comes 266.032, and the harmonic voltage across the capacitor and inductor is reduced to VSCH, and from this you can find out the value. Typically it comes to capacitor voltage 266.04 and RMS capacitor voltage percentage of this is hardly 104.74. So, only 4.7% voltage is there across the capacitor. So, voltage across the filter capacitor is higher, only 4.741, and therefore, this capacitor is selected a high voltage rating. However, the fundamental reactive power of this capacitor go to this, and where we represent the nominal as normal case. So, capacitor bank of 1097 kVAr had to now use in place of 1000 kVAr, and it means 9.7% rating had to be there for the capacitor bank with it. So, with this we like to conclude this passive filter. As I summarize, so passive filter are widely used to limit the harmonic propagation, to improve the power quality, and to reduce the harmonic distortion, and to provide the reactive power compensation and altogether. And these are designed for high current applications and high voltage like HVDC and high rating current source converter 1, and many such filters are in operation for HVDC transmission system, large industrial drive, static VR compensator, and these passive filters are also used along with the small rating active filter as a hybrid filter with major amount of passive filter, and these are the some of the references, and thank you.